They go and score on my house, right? Oh, fuck. What's his name?
Oh, okay, so I'm going to try something new. I'm going to turn the brightness down on here. Yeah. Okay, so the brightness was like reflecting off the screen, so I'm going to try it with no brightness on the screen. All right, so yeah, this is going to be a research stream. I actually made some pretty good progress the last couple days, so I'm going to go over a couple of the things I learned. I'll record this and put it on YouTube like usual. Right. So this is I'll be discussing something that was in my thesis. So this is I called them A configurations. So this will be research stream 6, and we'll call this A configurations. And we also talked about last time, I defined this psi-n map. So there's this map, which we'll talk about again today. Right. So the general process that we were going through was we had these perturbation differentials coming from this graph homology complex. So just to remind everyone, we had this double complex, which looks something like this. Right, and then there was a similar double complex, but instead of having Cartesian products here, we used the Alexander-Whitney map, and we wanted to perturb this complex to a new complex. But then the perturbation limit says we have to add these higher differentials. So essentially there's this Alexander-Whitney map here for all of these Cartesian factors. Here it's just like the identity, right? But in general, it will split Cartesian products into tensor products. Hello. I'm just looking at the chat. Oh, I got a raid. Thank you. Did not see that. Thank you, Slim. Right, so so yeah, basically we're going to talk about these two things today. These I basically invented, this notion, this A configuration notion, and this psi-n map, we're going to try to spell it out. I don't have it perfectly formal yet, but it's going to involve the first thing, the A configurations. So we have this double complex. There's some differential here based on the data in the graph. So we have some graph. Maybe it has some vertices like this, right? And depending on the edge information in the graph, it gives us information on, or it determines the differentials in this chain complex. And this goes all the way up until we have n factors, n number of these factors, however many vertices there are in the graph or whatever. Yeah, I mean, this could be yeah, it doesn't have to be a tree, but it could be like a closed graph, something like that. But and sorry if I don't talk too much to the chat. I'm like really focusing on this stuff. I've been working this out on my notebook all day. So yeah, that's the this is the overall setup. We have a certain chain complex which is built out of these Cartesian products. M is some simplicial set, and essentially things are too hard to compute here, so we want to just use the chain complexes on M itself and tensor products. This is a much easier thing to compute with. But the problem is once we apply this Alexander-Whitney map, we basically lose some of the information because this is only a quasi-isomorphism. So it essentially, yeah, there's these higher differentials that need to correct for the fact that this is not like a straight up isomorphism of the chain complexes. So yeah, that's essentially the setup. So then let me define. Yeah, I mean, if there's any questions, please don't hesitate to slow me down, stop me, ask as many questions as you want. But this is the main setup, and then we're going to talk about some tools I've come up with for how to compute what these higher maps are coming from the original chain complex. Okay, so I'm going to define something. So this will be pretty formal definition. I've sort of defined this thing before, or at least we've tried to talk about it, but here I'll give like a really formal definition. So this is that Barat-Eckley space, the space made up of the tuples of permutations, except I'm going to throw in partition information as well. So I call this BE up, like an upgraded version of the Barat-Eckley space, operad. So what are the D simplices of this space with arity K? So normally we have no partition information, but here I'm just going to say that this has elements which are of the form so again we have tuples of stuff. So it's a D simplex, but now, so these are all permutations, but they're permutations of a partition of 1 through K. So for instance, and also I'm going to add an extra stipulation, which I haven't really talked about yet, but I want each permutation to be a permutation of a refinement of the partition of the previous one. So essentially, what I'm saying is that Wi plus 1, so where Wi plus 1 is a permutation of a refinement of the partitions in Wi. Meaning that like if W0 is say it's a permutation of like the partitions 1, 2, that's the first partition, and then 3, 4 is another partition. So I have two partitions, so W0 could be like, let me just give an example real quick. So we could have something like 1, 2, 3, 4. That's one permutation, that's W0. Then maybe W1 could be 3, 1, 2, 4. So here W1 is a permutation, and the partitions are a refinement of the partitions from W0. Since, you know, like 1, 2 is a refinement of, before we had 1, 2 in the same partition, now 1, 2 are in separate partitions. So it's a refinement. We could, for instance, have like 3 and 4 still together. That would be okay. Are there any particular M's when AW is an isomorphism? So AW is only an isomorphism on the degree 0 part. It's, let's see. Yeah, it's only an isomorphism on the degree 0 part, and also if you only have one factor, then AW is just the identity map, so then it's an isomorphism. But that's kind of like a boring example. Right. Well, let me erase this example because we'll do more of these. But essentially, all I'm saying is that these are permutations, but they're permutations of partitionings of 1 through K. And so here K would be 4, for instance. Yeah, we'll see more of these. So let me just erase this because don't want this taking up too much room. But yeah, this is important, that Wi plus 1 is a permutation of a refinement of the partitions in Wi. So basically, we're getting more and more refined as we go down this to the right. That's the idea. Okay, and then basically I'm going to define, if I have an element like this W, I'm going to say how it can create an action in this Cartesian product thing. in the chains on the Cartesian product. Okay, let me just slow down a little bit. Is there any questions? So yeah, the problem is that AW is a quasi-isomorphism, but it's actually usually very far away from being an isomorphism. So essentially we need like a lot of these correction terms, which is kind of like one of the more annoying parts of the problem. But there's a lot of correction terms that are needed essentially. So yeah, this will be the key object, and I will define how, if you have an element of this form, some W, and it satisfies, you know, this refinement property, I'll say how it gives an action. So it'll, yeah, let me write it down right here. Let me just keep that up there for a second. So if I take one of these elements W, essentially there should be some map. Actually, this is the cyan map, right? So this is what we're trying to define. Cyan is a map from, so basically we're getting an action where elements here, the W's that we were just talking about, you take a simplex sigma in here and we send it to, we get something inside this Cartesian product. Yeah, I just want k of these, so I'll just put Cartesian to the k. So k factors of m, Cartesian product. Of course, we're always working in a ring, like some ring with unity R, commutative ring with unity. This is the coefficient ring. So commutative ring with unity. So everything here is like tensor product over R, you know, chains in M with coefficients in R, etc. Same with this one. And this thing should be like an R coefficient version of the BE. So basically it's like the integer version and then you tensor product with R. So just extend the coefficients. Right, so we've defined precisely what this object should be, and then now we just have to say how these elements act to give us things in here, and this action should be what we get from the graph homology correction terms. So that's the trick here. We need to figure out how to define this cyan. So that, again, remember the last time we had all these operations, the deltas, the she's, and stuff like that, and they operated in here. And we were sort of trying to get a relationship with, if I could do all the operations in BE and then apply some cyan map that agrees with everything as if I had done all the deltas and she's on the M part and ignored this. So this is basically our dictionary that goes from the operators, from the information in the operator side to the actual action that we get from the graph homology correction terms. And so I'm not going to define this precisely yet, but let's just say that it gives us some sum over, so I take an element W, the one we had written before, and it's going to give us some sum over A configurations, which I'll define in a bit. Okay, so it'll be like some, well, yeah, we'll fill in the blanks in a second, but so yeah, that's the idea. We're gonna take, actually, I guess I should write like W tensor with sigma, right? So it's going to take an element W from this space. It's going to act on some simplex sigma, and just like the action for surjections that we wrote a couple times back, maybe it was lesson the research 4, research 3 stream. But if we had this surjection operad and it acted on simplices similarly, except that we got the output space was tensor products, not this space. So this is in some sense like a generalization of the surjections operation, because these A configurations are in some sense a generalization of the action from the coaction of the surjections. Let's see. Right, so whereas over here we have basically permutation information, the coaction inside of here, you get something a little bit weirder. Right, so maybe I should say what an A configuration is, but I think I might want to go through an example first. Let's see. Okay, yeah, actually, so before we define A configurations, I'm going to, maybe I'll write down a couple, or actually, let's just look at the EML map of the surjection action. So I want to point something out first before we try to specify exactly what this map is. I want to give some motivation, or at least some examples for like what these A configuration things, like why this construction makes sense or is like natural in some sense. And also, yeah, so these A configurations, these were first defined in my PhD thesis. If you look it up. So it's I think it's called like on the graph homology with integral coefficients. So you'll see some more formal definition, but so let's just look first at, I want to look at an example. So let's recall what the action, we had surjections action. So this was one of the surjections. It acts on a simplex. Sigma, this got sent to, and remember we got this sum over these overlapping partitions. It was like a sum, there's like a sign here, which I won't, let's just leave it out for now. And we're gonna split it into 4 overlapping partitions, so like A1, A2, A3, A4. And I'm gonna stick the second and the fourth one in the second coefficient. A3 is gonna go in the third one, and A1 is gonna go in the first one. So it'll be like a sum, I wanna write it here, but I'm running out of room. Give myself a little more room. So this will get sent to a sum, some sign depending on the overlapping partition, but it'll be sigma of A1 tensor sigma of A2, A4 tensor sigma of, and then the third one gets A3. Are there any questions so far? So we did this a couple weeks ago. It just says you take any surjection, you know, of 1 through k. So in this case, k is 3, and we get a coaction on a simplex. We get this sum over overlapping partitions, and we split, you know, whatever the size of the simplex is. If it's a D simplex, we split like 0 through D into an overlapping partition with 4 partitions, A1, A2, A3, A4. And then we do a sum over all those possible overlapping partitions, and we stick the AIs in you know, the position that's corresponding to whatever the surjection says. So A2 and A4 go into 2. Yeah, like I said before. So yeah, so what happens? I guess the question here that I was interested in today, and sort of gives us a hint. I sort of already knew this, but working it out a little bit was helpful today. So the question is, so what kind of structure is it if we take the EML of this coaction? So what is EML of this thing? This yeah, the output here. And remember, EML is this map, which is one of the maps that goes from tensor products back into Cartesian products. So EML is a map from like C star of M tensor some amount of times with itself, and then we map into Cartesian products. Okay, and it turns out that I noticed today that you can actually write this as a join of certain things. So I want to make that a little bit clear. So I found some, well, yeah, let's just write it in this A configuration notation. So this is kind of notation I just invented. But so when you just have a single variables here, the notation is like perfectly makes sense. There's no ambiguity here. You just have to be a little bit careful once we get to the partition stuff, so this upgraded stuff. But here it's pretty obvious what this looks like. So if I write the the three factors like this, like 1, 2, 3, then the first one has A1 in it, so I can write it like A1 is in the first factor, A2, A4 is in the second factor. And remember, all the degeneracies are like, in some sense, shuffled between all of these factors. And then the last one has A3. So once I shuffle everything together with this, you can call this the shuffle map if you want, EML, shuffle map. It shuffles all of the tensor factors into a single giant Cartesian factor, this thing. Right, so there's actually a way to view this as a join of two different simplices in the Cartesian product. So this is actually equal to, again, this is like a sum over these guys, right? So there's still summing over all of these. But there's actually a way to write this as, again, it's a sum over some overlapping partitions. I'm leaving out the, the negative signs. Let's just make that clear. But yeah, there's actually a way to view this as two simplices in the triple Cartesian product actually joined together. So you can actually split the rows that don't have extra A's, meaning that 2 has 2 A's, but 1 only has 1 A. You can actually create another A just by taking A1 and splitting it into A1, A2. So really we can rewrite this as like A1, A2, A2 is now called A3, and this is A5. And then A3, I need to give it an A4, so then I need to relabel everything. So this should be A4 and A5, and this should be A6, actually. Okay, so the whole point of this was, I was trying to say, so we take the shuffle map of this tensor stuff. We get these like A configurations, so you can think of this as some sort of A configuration. But it's actually the join of these two EML maps. So we take A1, A3, A4 in the first position. We take A2, A6, A5 here. That's right, right? 2, 3, 4. Yeah. And then we apply this join in the middle. So sometimes I'll write this as like a star. But the point is that in the Cartesian space, you can sort of view this as an action of the table completion of this surjection. Or you can just think of it as it's an A configuration. It's 1, 2, 3, 2. It's A1 here, A2 is in the second position, A3 is in the third position, and A4 is in the second position. So A configurations are defined very similarly to the surjection action, except now we have all these degeneracies that allow us to be in this Cartesian product instead of in here. Yeah, I don't know. I thought this was interesting. I sort of noticed this earlier, that you can rewrite all of these EML maps as joins. So yeah, there's a very nice relationship. I didn't really have enough time to write it out today. Maybe I'll do something about it next time or whenever the next research stream is. But yeah, there's definitely a translation between table reduction, table completion, and this EML map and the AW map. So they're very analogous in some sense. And there's actions for both of them in the Cartesian product, and surjections act this way, and once we take their table completion, there's a way to describe the action as this join of these things. But these are actually the same thing. So it turns out that the action is just two different ways to describe the same element here. I'm not so sure yet how useful this is. Maybe, I think we can just do everything with A configurations and we can kind of ignore this representation anyways, but this might end up being useful for the proof, so I don't want to count it out completely yet. But yeah, so A configurations was this notion that I came up with. It's essentially like one of these surjections, or the EML of one of these surjection operations, except that the AIs are allowed to take up more than one position. So here they're always in just one column, or sorry, they're only in one row at a time. Like A1 is only in the first row. It doesn't show up in any other rows. So I thought what would be a cool generalization of that is if we had a similar type of object, I'll call it an A configuration. It's just like the EML of these surjection operations, coactions, except the AIs can now take up multiple rows. So I thought, why not, basically the same definition, just allow the AIs to take up multiple rows. So that's the only difference. Right. So then what's going to end up happening is this upgraded BE element, the cyan map, is going to give us an action. It's going to act very similarly. Surjections act on here. They give us tensor factors. But the upgraded BE elements, they're going to give us A configurations in this Cartesian factor. So instead of the normal surjection operation where we end up here, we're going to get some sort of upgraded action, and we're going to end up in here. In the tensor factor, in the Cartesian factors, I mean. And hopefully we can prove, we won't be able to prove this today, of course, I haven't written it out fully, but I think we have all the tools now where once we define this cyan map, it'll just be a matter of proving that the cyan map is actually corresponding with the actual graph homology A configurations. Okay, so let's see. Any questions? I'm not getting any. Yeah, no questions in the chat? Okay. Okay, so yeah, let me just go over the full picture first. Okay, so the initial picture is we're dealing with correction maps which look like this. So we have a map into C star of M times M, and then we apply the Xi homotopy, the little h, right? Oh, sorry, I want to say that this is a homotopy, so it's a map from this chain complex to itself, but it changes degree by 1. So this is a little h, and I'll write like a little +1 here maybe. Then we go to 3 factors and etc. until we keep applying these h's each time after the delta maps, and then we finally end up with n factors, however many vertices there are in the graph. Right. And then we apply AW at the end. So that will give us our correction terms. Surjection operations, coactions. Oh, we got a Banovator. Right, so these are the maps we're trying to figure out what they are, right? We have a bunch of delta maps here, right? We do delta 1, 2 here. So we create 2 factors, 2 simplices, sigma times sigma, or sigma comma sigma, in the Cartesian product. Then we apply the Xi homotopy H. Then we apply another delta map, which is the, coming from the edge contractions. That's our differential. Then we apply another Xi homotopy, and we keep going until we finally get to the full n factors here. So there's n of these. And then to figure out what the terms are, we need to apply the Alexander-Whitney map, and this will allow us to push down to the actual chain complex we want to work in and allow us to get our correction terms. The only problem is it's very hard to keep track of what these maps are doing without the extra stuff that I've been working on. So the stuff I've been working on says, okay, well, let's view this. Instead of viewing C star of M just alone, let's give it basically like this upgraded BE thing to work on, except when we just have one element, it's kind of boring. It's just BE upgraded of 1, which is just a point, but that's fine. We're going to do operations on it. So we're essentially just going to send a simplex sigma to a sigma tensor with this point, this single point. But now instead of applying delta 1, 2 to M, we're going to apply it to the operation. So there's going to be a bunch of delta 1, 2 tensor identity maps, stuff like that. And this will end us up in BE star up of 2, tensor C star of M. And basically it's just going to keep going up like that, just like before. And then finally we'll end up in BE upgraded of N, tensor C star of M. And then we want some sort of reconciliation here to these correction terms. But the thing that we talked about last time is there's some psi n map that should go here that sort of translates this stuff into what we should get over here. Okay, and this was our psi n map that we haven't really fully defined yet, but we've given you examples, or I've given you examples of A configurations, and we've said that psi n should be some sort of sum over different A configurations in this Cartesian factors, in this the chain complex on these Cartesian factors. So I think I've done enough calculations to be pretty sure of this, that once we get this A configurations map down correctly, then it'll just be a matter of showing that for every A configuration that we have here, if we apply the Alexander-Whitney map to it, it just simply reduces to the coaction of the table reduction of whatever's over here. So that's kind of what I went through in the last video. We were just going over, we didn't actually define this psi n map, but we said that we think it should exist, and if it exists, it should have this property where I can either go here and then apply AW, or I can just take table reduction and then take the coaction, and this diagram should commute. I can either go here first, then apply Alexander-Whitney, or I can just apply this the coaction of the table reduction of whatever these BE elements are. Okay, so maybe just as an example now, let's try to, let's just write down an element in here in this BE thing, and I'll give you the example of how it acts in here and gives us A configurations, and then I'll sort of give you some intuition for why the Alexander-Whitney map of that A configuration should match with the coaction of the table reduction of the element that we started with. So that will be the example, and then I think I can just talk about that a little bit, and then I don't have too much, I think, to say today, unless there's questions. But I just wanted to get through what the psi n map, at least intuitively, should be, give you some examples of these A configurations that we get for some of these things, and then just give you some intuition for why the Alexander-Whitney map should match up with the table reduction. Hello, Eve Raven. Haven't seen you in, well, it's been a couple days, maybe, or a week or so, but welcome. Right, so is there any questions? Is anyone confused about, at least anyone that's, still following? Hello. Oh, Penn Center. It put your text as purple. I thought you were also E-Raven. So I'm just gonna keep going unless someone stops me. So if you want me to explain any of this more, definitely let me know. But instead of explaining this explicitly, I want to basically just show you an example where we go here first, then we go here, and then, or we can just go here, and I'll show you that they're the same thing. Yeah, okay, so this is an example from my PhD thesis. This is one of the most simple cases of the graph homology correction terms. I am incognito. Yeah, I've noticed Twitch, like, sometimes it changes the colors of people's names, and like, so like it could be one color and then you look in another browser and it's a different color. I don't get it. Not that it's important, but I like to, it's good for keeping track of everyone, but you know, they just randomize all the colors, so. Okay, so this is one of the A configurations that comes up from my thesis. Right, so this is like Levy, I guess, like 2021, I guess. You know, I think it's called like graph homology complex with integral coefficients. Right, so this is just the, this is just our map delta 1, 2, little h, so delta xi, or yeah, delta 1, 2, little h, which is the xi homotopy. Then we do delta 1, 3. So this corresponds to this graph where we have 1, 2, 3 here, and 3 is collapsing into 1 first, and then we collapse 2 into 1 after. So, yeah. Right. So then in the thesis, I go through this one's actually pretty easy to calculate. For 3 vertices, it's not too bad. You can show that if you apply these maps to sigma, then what do you get? So let's just go through it slowly. So you copy sigma comma sigma, right? You get a simplex in the Cartesian product. It's just sigma comma sigma, very simple. Then we want to apply h to this, and then delta 1, 3. When we apply h, we're going to get an A configuration. This is going to be delta 1, 3, and I'll write the A configuration in that notation like I had before. So this will be like A1, A1, A2, A3, like that. Remember, so this is just like the EML of a surjection coaction, except that the AIs are allowed to take up more than one row. So this is like A1 here and A1 also on the bottom. So it's slightly different than the EML of the coaction of some surjection, because for those, the AIs are only in a single row at a time. But here we have an A configuration, so A1 is here, A1 is also here in this row, and then we have A2 here and A3 in the second row. If I apply delta 1, 3, that just means I copy the first row to the new third row. So this will be just a new A configuration. It'll be A1, 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 A2, A3, and then A2 also, like that. And of course, you know, remember we have like a sum here. Just put a sum sign. Okay, so how are the chickens? They're doing well. Yeah, one of our chickens actually got attacked by a hawk the other day, but she survived. So, I don't know. Tough chicken. Right, so the question is, so what should the AW of this map be? That's the big question. So that's the $1 million question. What is the AW of this map, of this A configuration? And not only what is the Alexander-Whitney map of this sum of these, the terms that look like this A configuration action or coaction. So not only what is the Alexander-Whitney map of this, but how can we view it as the coaction of some table reduction? So we can actually split this just like we viewed the other one as a join. We can look at this as like the coaction of some, basically surjection. Except now the surjections are of partitions because the AIs can be in multiple rows at the same time. She won in chicken versus hawk. Yeah, my dog sort of helped out though, so not so sure I would root for the chicken over the hawk in general, but okay. Yeah, so that's the main question. So what is the Alexander-Whitney map of this A configuration, and how could we see this as some table reduction coaction? So let's just look at this one example. I'll rewrite this A configuration, but let me erase everything else. Squeaky eraser. So here's the million-dollar question. What is Alexander-Whitney of this sum of A configurations? We have some negative sign, which depends on the overlapping partitions. And then it looks like A1, 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 A2, A2, and then A3. So there's actually a way to go, there's actually a way to view this element as the coaction of some, some surjection, or also actually equivalently, so surjections are equivalent to their table completion. Table completion is basically an embedding of the surjections into this BE operad, the bigger one, the one that's all permutations. Another way to view that is I want to view this as like a join of things. So if I can rewrite this, it's just another way of viewing the same. Everything here is the same. I'm just going to write it slightly differently. So instead of this way, it's going to be A1, 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 join. And now here it's going to be A2. Oh, actually, yeah, so this is kind of boring. I'm not really writing anything too interesting here. The point is, though, that it's one permutation joined with another permutation. So the permutation is one partition, just 1, 2, 3. So it's like 1, 2, 3, all in the same partition. And then the second permutation, I can view it as 1, 3 joined together in a single partition, and then 2 is alone. Okay, so one way of viewing this A configuration is that it's like the coaction of this particular BE upgraded element. It's upgraded because there's partition information. The fact that 1 and 3 are in the same partition, and the fact that these are all 3 in the same partition, that means we're in this upgraded version. So the theorem, or the conjecture that we're trying to prove as a theorem, is that if I take the Alexander-Whitney map of some A configuration with this setup, it should be the same thing as the coaction of the table reduction of this element. So if I view this as just a normal element in this Barat-Eckley, so it's just 2 permutations, and if I look at the table reduction of that, so 1, 2, 3, 1, 3, 2, then I actually just get 1, 2, 3, 2. Because it's 1, I would get 1, 1, 3, 2, but that's degenerate. So then I also get 1, 2, 3, 2, and then 1, 2, 3, 3, which is degenerate. So this is the only non-degenerate surjection for the table reduction of this, which makes sense. Actually, no, let me not say that. That probably isn't right. Right. So if everything works out the way I think it should, then when we take the Alexander-Whitney of all this A configuration stuff, we should just get the coaction of 1, 2, 3, 2. So we should just get this sum like before, where it's sigma of A1 tensor sigma of A2, A4 tensor with sigma of A3. in that order. And that's essentially how this theorem should work. It should say, okay, we have a bunch of upgraded BE stuff. We can convert all of that information into what's actually happening on the Cartesian factors for the correction terms, and that gives us all these A configurations. And if I want to know what's the Alexander-Whitney map of all of those A configurations that I get for the correction terms, well, I can just take a table reduction of some element that's coming from the configuration of the A's when I go from left to right in the joins. And if I look at the permutations for each join, then if I take the table reduction of that, that should correspond with the action once I would take this Alexander-Whitney map. So it's pretty convoluted to think it through, but I'm trying to simplify things in the sense that there should just be like one thing you have to look at. You do all your operations in this upgraded BE thing, you take a table reduction at the end, and that should be all you have to do. And then the theorem that proves that what we get is correct, that depends on this psi-n map being correct. If the psi-n map doesn't make any sense, then this table reduction could just be giving us garbage. And if the psi-n map is, not agreeing with the Alexander-Whitney map at the end, then again, it's just giving us garbage. So we still have to prove that once we define this psi-n map, that it makes that diagram that I erased before actually commute, that I can apply psi-n, get A configurations, and then apply Alexander-Whitney and be sure that I got the correct terms. Or I could just do like what I did here, take a table reduction, and the coaction of that is the answer. Yeah, so we just have to prove that that's actually true. So everything here is well defined. We can always do all of these operations. We can do the deltas on the upgraded BE. We can do the Xi homotopy on the upgraded BE. And then we can take a table reduction at the end. We just have to prove that it actually matches with the correction term, with the coaction that we get from the graph homology stuff. So that's basically it. Once we prove that, then this paper should essentially just be done. It'll just be, yeah, you get any graph, you try to compute the graph homology, you get a bunch of deltas, Xi's on the operator side, you take a table reduction, and that should be the answer. We just have to prove that it's correct. Okay. So any questions? And then I guess I'm trying to think what else to say here, but it's kind of hard to keep going with my brain all fried. Yeah, I want to give you like generalizations on like, if we get this graph homology complex, all the correction terms down, what could we use this complex to compute? And there's a little bit like higher algebra stuff that I might want to go into eventually, but I'm not going to have time today. But yeah, there's something called factorization homology. And we think that if we get all these terms and we take some sort of limit, we should be getting the homology of the factors. We should be getting the factorization homology of whatever the manifold or space we're working over. Right. Let me see. What else do I want to say? Oh, right, yeah. Let me give an example. So we've showed, or I've given you an example of where we get A configurations naturally from the graph homology correction terms. I mean, I haven't proved that, the AW of this actually is the coaction of this, but you can sort of see why it would be true. You get a piece of the A1 here, right? Then you jump down here, you get a second piece of A1 that goes in the second component, so that's this A2. We also gain the full A3 here, so that becomes A4 because we split A1, so we get another, we have to relabel, this becomes A4, so this is A2, A4. And then now this new thing, which is now A3, goes in the last one, and that's how we get A3. So you can sort of see how, if you take the Alexander-Whitney of an A configuration that looks like this, how you might get these terms, at least for this simple example. But my conjecture says that this is true in general, that you'll get a bunch of these BE elements for every one of these A configurations, and if you want to take that Alexander-Whitney, you can just take the table reduction instead. Right. Yeah, so what I wanted to say before was let's do an example where we take an upgraded BE element and then we produce some A configurations from it. So that will be this an example of this cyan map that we're trying to define formally. Okay, so the cyan map should be defined for any upgraded BE element. So any upgraded BE element should give us some sort of coaction, or at least it should give us a map here where we take one simplex sigma and we get something inside this Cartesian factors, or there should be k of them. Okay, so let's just do an example, and you'll see sort of how this cyan map is related to the normal table reduction coaction, or the normal coaction by surjections. Right, so I actually didn't write one down here. I'm just going to kind of make up one. So to be in this space, remember it needs to be a refinement of the partitions from left to right. So we can't do, for instance, we can't do an element like 1, 2, 3 as the first permutation, and then the second one just 1, 2, 3 as a single partition. This is not allowed. Because this is not a refinement from left to right. It's actually a refinement from right to left, right? This partition of 1, 2, 3 is a refinement of this one, not the other way around, right? So we want to be getting more refined as we go to the right, not the other way around. So this is not allowed. But we can take anything, as long as it's a refinement from left to right, then we're fine. So you could have something like, did I have an example in here or no? Forget if I wrote down one or not. Okay, yeah, I think, yeah, so here's, I don't like this one. Yeah, let me do a simpler one, just, I don't want to start out too complicated. Okay. So first notice that it is actually in this, so tensor sigma, right? It's gonna give us something. Just first notice that this actually is an element in here. So it's a 2 simplex, right? This the 0th vertex, the first vertex, and the second vertex. So it's basically a triangle in this space, and it is a refinement from left to right, right? Because here we have partition 1 and 2 are in the same partition. Here they're split, but it's not like 2 became inside the partition of 3, right? So it is a refinement. Every partition is either the same or more refined. And same with this. This is the same partition as this, so it's fine. It's a refinement. And so what is the coaction? There's going to be, basically we're going to get A configurations, but I'm going to start counting how, similarly to how the table reduction map works. So it'll be like, this will be A1, and I'm not going to go to the second one. I'm just going to skip down to here. So this will be A2, like how the table reduction map, you go to the next element, and you just go to the first one that hasn't been passed over yet. So we haven't passed over anything yet. So the first one is just 2. Now I skip down again to 3. So this will be A3, then A4, and A5. So that's the first A configuration. So it'll be a sum over -1A, and then it looks something like A1, A1, A2, A3, A4, A5, like that. So it's very similar to the EML again of sigma of the AIs, tensor or something, except now again we have an A1 here and an A1 here, so there's kind of like a duplicate information here. So yeah, this is one of the terms, but actually we'll get more terms. So remember the table reduction map, there's more terms because you don't have to skip to the next element for each row. You can actually start going here, but so there's another term that looks something like, again, it's similar, except now it'll be, so let me erase the AIs here and we'll look at the next term. So here, let me do A1 here, then we'll do A2 here, and then I'll actually skip to A3 at the 1 here. But that means now 2 is sort of canceled. And now when I go to the next one, I can say that this is A4, but then we skip over 2 because it got canceled here since we went to 1. And then the A5 should be just 1. So we have another A configuration, which is A1, A1, A2, A3 up here, then A4 down here, and A5 back up here. So this is another A configuration. Notice that it actually is different than the first one because like the A4 is in the third here and here it's in the second position. And then yeah, you just basically have this upgraded table reduction map where it's very similar to the normal table reduction map, except when you go past a certain partition in a certain permutation, that one gets canceled and you can no longer use it in the subsequent ones. So here, there's another one, like if I go 1, 2, and then I go over it, and the next one is A2 at 3, then the 1, 2 will get canceled, and then I can't use 1 or 2 in the subsequent AIs. But yeah, there's basically a bunch more terms. I don't want to write out all of them. I just made up this one, so it actually has more terms than I thought it would have, but we did out the first 2, so you can see how you would get these A configurations. There'll just be more of them, but it's just a process of going through this and taking this upgraded table reduction map. Okay, so that is the cyan. So it's basically going to involve this sort of, it's a certain coaction, but it exists with these delta AIs. So it's a little bit different than the normal EML of the coaction, but it very, 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 very similar. And you can get all of the A configurations from the information in this upgraded BE element, just as we were doing it here to get these A configurations. All right, so that's basically the name of the game. We're just going to get a bunch of elements in here from all of the operatic delta, the capital HC, all the compositions of these like deltas, everything that we would normally do just here, the delta, the little h, and the Alexander-Whitney map at the end. Instead, we push everything to the coefficient side, and we have an operatic delta, we have an operatic xi, which we write as capital H, and then instead of an Alexander-Whitney map at the end, we have this table reduction map. So it's this versus on the non-operatic side, we just have the regular, so I'll write operatic here just to remind us. And then we have the little h, which is just the regular xi homotopy, and then we have the Alexander-Whitney map at the end. But remember, these are somehow related to each other in the sense that I've been describing right here, where if you add on this coefficient piece, then whatever you were going to operate on here with the delta, little h, and AW, all the stuff you were going to do here, you just do it here instead. And the theorem, the conjecture, or theorem, if we prove it, is that everything we do with these, if we take a table reduction at the end, I should get the coaction. It should match up with what I get when I take an Alexander-Whitney map of like this stuff, the A configurations. Oh yeah, I'm not going to uni. No, don't worry. This is graduate level math. You wouldn't be you wouldn't even be expected to learn this, as a graduate student, unless you wanted to specifically study this particular mathematics. So if you are going to university, don't worry. It's definitely not undergraduate stuff. It's not even really graduate stuff. This is like research level stuff, right? Unless you're researching this, right? Okay, so I guess next time I'll maybe go a little more in depth, or maybe we'll try to define this cyan a little bit more formally, but I have done it in my notes. I just don't think I'm prepared to really present it yet. But yeah, that should be the whole story, essentially. All of the graph homology terms are compositions of these delta little h and AW at the end to get the correction term. And our conjecture says, it's sort of hard to keep track of what's going on here, but we can translate everything into this upgraded BE story. And if we take a table reduction at the end, the elements that we get, which are surjections, if we do the coaction of those surjections, it should be the same as the terms as we get with this Alexander-Whitney map, which maps from here into the K tensor factors. So into C star M, tensor C star M, tensor C star M, K times. So basically that giant diagram I had before, it's just saying that huge one commutes. If we go up the right side, we're in this picture. If we went up the left side of the picture, we were using these maps. And there's a reconciliation at the end, which says that all the terms, if I take the Alexander-Whitney map, which is everything that I want on the right, it's the same, it matches up with the table reduction of everything on the left. And the cyan map is sort of the translator between the two that goes from the operatic information to the actual delta sheet terms in the graph homology correction stuff. So this should be the key of the proof. The proper definition of the cyan, if it's properly defined, then the proof should just follow simply. It should just be, I go from here, I go to here, I take AW, I get my terms, and if I take a table reduction, it should be the same thing. Once we prove that, then we're done. So we define this properly, and we should be able to make the proof work that tells us how to compute these, what terms we're getting. Okay, I think I'm pretty much done. I went an hour, but I don't really have too much else to say. Are there any questions? So A configurations are very, very close to the EML of stuff, except we're allowed to have the AIs in multiple positions. But other than that, they're essentially the same. There is some stuff here we need to check, like that this table reduction of the upgraded version actually makes sense, so that we know which A configurations we're going to get. And then we also have to check that this, cyan map actually makes that giant diagram before commute. So it's possible it doesn't, or, maybe we can't figure out the proper definition that does make it work, but I feel very confident that just as I was able to find the A configurations here, it should work for any upgraded BE element, as long as these ones are refinements of the... Yeah, as long as it's a refinement as you go. Should make sense. But yeah, we need to make sure that all of this stuff is well defined and makes sense, of course. Otherwise, yeah. Otherwise, we're not doing math properly, right? Okay, let's see. Yeah, I think I basically covered everything I wanted to today. Yeah, I was getting some cool story I was going over in my notes with this table reduction, table completion, and this coaction inside the Cartesian product versus the coaction in the tensor product. And there's this whole relationship, very nice relationship going on, but I haven't really had enough time to write it out properly, so. Okay, I don't see any questions in the chat, so I'll just end it here. I'm gonna raid, let's see who there is to raid, but I hope you all enjoyed that, and yeah, you can catch it on YouTube if you, missed something earlier. So if you want to go back and see something I did earlier, check it out on YouTube, and yeah.